I'm working on this new PCB where I have a Raspberry Pi Pico acting as a USB keyboard and mouse. So on the screw terminals, I can hook in things like a trackball with those optical encoder discs or other similar things. Or it can even read in regular mechanical rotary encoders, as long as it's two inputs representing rotary action. Otherwise, the keyboard side of this, I have these joystick headers here. They're both 13 pins each, and they allow plugging in these rotary arcade joysticks where they have the 13-pin header. These are LS30 models, SNK, and there's also other compatible ones. I have a HAP controls one, so it's also got rotary switches on it that change their position as you rotate the joystick. So you can go up, down, left, right, as usual, and there's switches here, but you also twist this, and those directions are represented on this 13-pin cable. What this is all about is arcade emulation in software to play old games, but using real arcade controls. So the trackball interface is relatively straightforward in purpose. It's basically a mouse, so this controls a USB mouse when plugged into the computer. So any arcade games that used basically a mouse, a trackball, or games like Breakout where it's one axis of a mouse, they call that a spinner. So you can just go sideways, and on the screen the character at the bottom can move side to side and the ball bounces off of it. So that's straightforward to implement, but these joysticks may need a backstory. Here's an example of an arcade game that used those yellow LS30 rotary joysticks. This one is Ikari Warriors. There's a bunch of others. Another one I used to play in the arcade was Guerrilla War. So these joysticks can just move up, down, left, right to move the character, and you rotate this to change the direction the character is firing. So here's one screenshot of that game. The character currently is facing forward, so if he fires, the bullets or grenades are going to go straight up. He can still run sideways and be shooting straight up until the joystick is twisted. In this picture, he's aiming diagonally up. So there's a bullet firing that way. And so if you move the joystick so he starts running up this way, he's still firing diagonally. So you go up here and you're firing this way and you can shoot these guys. Then if you get to here, you can rotate the joystick so you're firing straight and get him. So if we want to emulate those old arcade games using MAME, all the controls for this game will be basically keyboard key presses. So all of these buttons for fire and bomb and player one start and whatever, even the joystick up, down, left, right, those are all keyboard keys that we would read over USB. And with this joystick having the extra rotate feature, the original arcade looked at these 12 discrete inputs and it could tell exactly where is this positioned. So you can rotate this in 12 positions to go fully around the circle. But that's a lot of keys. If you have two players, that's 24 inputs just for these positions, plus everything else you need. So the emulator only cares when you do make a move, did you go clockwise or did you go counterclockwise? And so they have just two inputs on the keyboard that they're looking for to tell if this is rotating, and if so, rotate the character on the screen. So with this board, I can plug in two joysticks to support two players, and as soon as one of these joysticks are rotated, the Raspberry Pi Pico will do a calculation on here, figure out did it just move clockwise or counterclockwise, and send out a keystroke to represent one direction or the other has just been moved. So this board will allow playing two-player games that used this, or playing trackballs or other similar games as well. And the scope of this whole project here is only to handle those special rotary controls, not the regular up, down, left, right. It's more like an add-on to plug in over USB, and it just shows up as another keyboard and another mouse to work alongside other existing ones. And normally for the regular buttons and joysticks, You still need some other sort of dedicated USB or whatever interface you want for a keyboard with a whole bunch of other screw terminals to hook up the other joystick and buttons and create some sort of a controller. This is just for those odd cases where you may have a special need if the regular controller you have doesn't support these kind of features. Starting out looking at the trackball mouse interface, because you can move up and down or left and right with the mouse, there's 2 of these encoder discs in there, and there's going to be an infrared transmitter and receiver pair so that as this is rotated, in this case when you move the ball around, at some point a beam of light can shine through one of these openings, and right next to it another beam of light gets blocked. So as you rotate, 2 sensors are going to see light or see darkness, and based on the way that occurs, you can tell if this disc is going clockwise or counterclockwise, and if the mouse cursor should go up or down in one case, or left and right for the other case, or diagonal if both encoders are moving at the same time as you go in that direction. So here, in this case, we have the one encoder disc here and another one in here. So as we move the trackball in various directions, the encoders are going to move, and we can tell if we're going whatever direction. So on each encoder for the X and the Y axis, there's a 4-pin connector, 5 volts ground, and 2 outputs for those 2 sensors to detect which way you're going. So it comes out to this, in this case, a 6-pin connector. So black and red are the power, and then there's 4 signals. The power gets split and goes to both sides. Then you got 2 signals here, 2 signals here, and then these 6 pins. I bought a mating connector here. This one I got on Mauser. It has these extra interlock things that aren't really used. This side doesn't have it, but it's the right kind of connector. So if I plug that in, now I'm providing 5 volts and ground from this board, and I've got 4 signals I can read in to tell the X and Y axis movement here on these inputs. Different trackballs may have different kinds of connector hookups, but it just turns out that this one here matches 6 pins that I have. So there's 5 volts and ground, and then there's an X-axis and a Y-axis on these pin numbers. But if you don't know which axis is which, and which out of the 2 on each axis should be going where on any given circuit, all we need to make sure is the 5 volts and ground are going where they should, and then it's a matter of you can pretty much hook up these actual signals in any order, and all that's going to happen is if you expect to go up, you may go down, or you may go left. You just do trial and error, worst case, hooking those signals up until things go the direction you expect. Or you keep it as it is and change the inputs in software, renaming them until it responds correctly. Down in the description, I'll put the part number for these connectors and the pins that go inside that you crimp onto the wires. I found them somewhere on the internet, so this is what worked for me just for prototyping this. And for getting these rotary joystick 13-pin connectors hooked up to this board, I'm just using standard right angle 0.1-inch headers. So the connector plugs in sideways instead of straight down. But these regular 0.1-inch headers, like you would see on an Arduino board, are not exactly right. That's a 2.54 millimeter pin-to-pin spacing. These were actually, I believe, only 2.50 millimeter. So it happens that these can connect here, and it's not the exact same size of metal contact. I'm just using it for my purposes because it does mate correctly enough to get working. But trying to research the exact connector if I wanted to put one on the board, I've seen different info all over the place. So here's an example of, I think, the regular 0.1-inch header, but that's a straight up and down version, not a right angle. That's basically what I'm using. And this green rotary switch here with all those pins on the bottom, that looks like what is here on this LS30 rotary joystick. So here, somebody gave some part numbers here. For the PCB side, the right angle connector may be this part number. So BS13 is probably 13 pin. SHF. I ended up finding this JST 2.5 millimeter pitch connector series, NH connector. Looking at this part number BS13 and then SHF, there's a BS13P SHF 1AA, and so that's a side entry version of this connector series, which is basically the right angle header, 2.5 millimeters between pins. So presumably that is the right connector, but trying to get these, at least in North America, seems to be difficult. So that's why I'm just using this regular old right-angled 0.1 inch, 2.54 millimeter header. The concept of monitoring these 12 input switches to generate a clockwise or counterclockwise output USB keystroke, I made a table here showing 4 inputs, A, B, C, and D. So first let's look at the schematic to see what that means. This is the schematic of that board, and for now, focusing on the right side for the joysticks, this is the Raspberry Pi Pico in the middle. What we're doing is taking the 2 joystick connectors and monitoring them where we're only looking at 4 inputs instead of all 12 on each one. And they probably could have been directly connected to the Pi Pico where the GPIO run at 3.3 volts, because all we're doing is connecting a ground or leaving this open circuit. So we would rely on internal pull-up resistors at 3.3 volts. But I wanted this to be buffered just in case anything went wrong. I would only risk damaging one of these level translating ICs instead of compromising a Raspberry Pi. If I were doing this for mass production, this is just extra parts. I wouldn't do it this way, but this is just the workbench. And I was already using this strategy on the other side of the board for the mouse related stuff, so it was easy enough to just duplicate it over here. So what we're doing is, since all of these inputs are either not connected to anything or connected to ground when that switch is being activated, we need to pull these signals up. So I'm just pulling them up to the 5-volt V-bus with these pull-up resistor networks. And when the rotary switch goes to a certain position, it connects it to ground and pulls this input low. So that's how we get our high and low at 5 volts. Then this 74LVC245 is acting as a level shifter. This runs at 3.3 volts, and there's a data direction pin here pulled to 3.3, which means this side with the A pins are inputs and the B side are outputs. So the inputs of this chip are 5 volt tolerant, even though it only runs at 3.3. So here's my 5 volt or ground inputs, and the outputs go between ground and 3.3 volts, which is safe for the Raspberry Pi. And I have these TVS diodes here just in case there is some static electricity or anything like that, a momentary high voltage spike, since this is all coming from long wires off board and anything could be going on there. So the reason we only have 4 inputs on each joystick when there's actually 12 physical switches, when we are rotating clockwise, so this is going like this, from left to right, these pins here are pins 1 all the way through to pin 13 being ground on the far right. So as we go clockwise, the switch that's getting grounded changes from 1 up toward 12. And if you then go 1 more, you've gone full circle and you start over at 1 and you keep going from 1 toward 12. If you're going counterclockwise, you're going to be going from 12 down toward 1. And then if you keep going, you start over at 12 and you keep going on until you get to 1 again. But we don't really need to monitor all 12. We could even optimize this down to just 3 inputs, but I found 4 works better. If you're going, say, from 1 to 2, you're grounding here and then you're grounding here instead. And then you switch to 3, you're grounding here. You switch to 4, you're grounding here. By the time we've moved that far, if we want to keep going clockwise, so now we're grounding pin 5, if we tie pin 5 in common with pin 1, then instead of going from 4 toward 5, we're going from 4 and starting over back at 1. Then if we're going physically on the joystick from 5 to 6, we're tying 6 back to 2. So what we've done is, instead of going 1, 2, 3, 4, 5, 6, we've gone 1, 2, 3, 4, 1, 2. And if we just keep going, it's the same as the fact that we go 1 through 12, and if we rotate yet again, we start over at 1. So it's just the same concept. We can go all the way 1 to 12 and then start over, keep going that direction. We're still going 1 to 12, 1 to 12, 1 to 12. So what's the difference if we go 1 to 4, 1 to 4, 1 to 4? We're just doing it more often because there's less pins, but we're doing the same thing. I found that trying to tie them so that it just goes 1 to 3 and then starts over at 1, you can spin this thing so fast that you actually wrap around if you're only looking at 3. So instead of going 1, 2, 3, 1, 2, 3, the inputs may only register 1, 2, 3, and you've gone so fast, it skips 1 and it lands on 2, and it looks like you went backwards then from 3 to 2. Counterclockwise, instead of continuing 1, 2, 3, 1, 2, 3, where you skipped 1 because you went so fast, if that makes any sense. So I just found that reading in 4 pins instead of 3, I can go reasonably fast and detect properly as I change directions within reason. So it's a way to save inputs on here so I don't need to monitor so many to get the same job done. So looking at going clockwise from position 1 through 4 in this case, really, if I call these 1A through 1D, meaning we're going clockwise as we go from A toward D, one thing to note is whichever switch we are actually landing on when we rotate, the rest are going to be pulled as a logic 1, and the one that's active is going to be a logic 0. So let's say I'm on position 1. 1A is going to be at ground, and then B, C, D are going to be at 5 volts. But in software, just to make it easy for the way I did it, I inverted all of this. So really, whatever pin we are currently grounding on the joystick, instead of a 0, I read it in and turn it into a 1, and all the rest are 0 when nothing is happening. Here's all the possibilities of one of these 4 joystick inputs currently being grounded, which would show as a logic 1 in software, and the rest are off. Or a different one can be grounded, which is a 1 here, and the rest are off, and so on. Going clockwise, we go 1 through 4, or A through D. So going A through D, if we start with A being the switch we are currently on, and we're going clockwise, that means B is going to be the next one to be active. Then if we still go clockwise, C is the next one to be active, and so on. So in this table, when we go from bottom toward the top of the table, we're moving clockwise. So in software, we can recognize that. If we are going counterclockwise on the physical joystick, if we start with pin 4 being the one that's grounded, and we go counterclockwise, we go to 3, and then 2, and then 1, and then start over at 4. So we're going input D through A. On this table then, counterclockwise is represented by going from the top of the table to the bottom. So if we start with input D being the one we are on, we go counterclockwise 1 step, we are on position C, then B, and then A. Then if we keep going another step counterclockwise, we roll over again, so we're back to D being the one that we're on. So in software, I'm reading in these 4 switches on each joystick, and it basically becomes a binary number. And in decimal, this is what those numbers would be. So when input D is the one we're on, software sees it as a decimal number 8, input C is a decimal number 4, etc. And what we can do is, when movement has happened, let's say we were in this state, so input B is where the joystick is currently rotated to. If we then move either 1 step clockwise or 1 step counterclockwise, we can compare the number 2 in this case against the number 4 or the number 1, and we can determine which way we went. So if we say we were on this number 2, now I move to this position, I've gone from input B to C. If this is my current position and this is my last position, I can say if my last position minus my current position is negative, then we've gone in this direction, which is clockwise. 2 minus 4 is negative 2. Likewise, if we were here on decimal 2, but we moved the next position counterclockwise, the last position of 2 minus current position of 1 equals positive 1. So we know if the result of that is positive, we went counterclockwise. Now, the only problem with that is because we can keep going after we get to a lower and lower decimal number, we can still be going in this direction, and the next valid state gives us a suddenly higher number, so the math on that would fail, just simply subtracting the current and previous numbers. So really what we need to do on top of that subtraction is double check, did we just get to one of these extreme ends where we actually wrapped around and we need to handle the calculation slightly differently? It starts to get a bit complicated to try and explain it. I did look at this in a previous video years ago. I don't know if I did a better job then or now, but I go more into detail, I think, about looking at these endpoints where we have to do extra observations on where we are and where we just moved to. So you can check that video if you want. But that's what's happening on these joysticks, monitoring only 4 inputs each, looking at what we were at and what we now are on, analyzing the situation, and figuring out ultimately did we go clockwise or counterclockwise. And just glancing over at the CircuitPython script for this, when we're reading the joysticks, we're doing that subtraction between the last position and the new position we just rotated to. And if that is not 0, it means we've either gone clockwise or counterclockwise because we are in a new joystick position. So if the calculation here shows a negative number or even a positive number, and we were at previously and now certain positions in that table where we wrap around in each case, doing all of this is ultimately how we would figure out on joystick 1 we went clockwise. So we send out a certain keystroke, this one's an X, over USB that the game emulator will see as clockwise rotation on the joystick. Doing similar things, we figure out if we went counterclockwise and send that keystroke, and then do the same thing on the second joystick. Looking at the other section of this schematic for the mouse or trackball inputs, we have a similar situation where we're dealing with 5 volts and ground, but this time those optical sensors do expect 5 volts, so we do need to do this level translating to get it down to 3.3 to safely interface with the Pi Pico. And again, I have these ESD protection TVS diodes in case anything's going on with static electricity. Especially with this, we have all this plastic and these moving parts. This even has a couple of wires here with copper, it looks like, foil on the plastic. I don't know where it goes anywhere else inside, but there's a grounding lug here to help dissipate any static. But in case of anything showing up on the harnesses, that's what these TVS diodes are there for. Otherwise, there's 2 kinds of trackball optical interfaces. Either way, there's either going to be, at any given time, an open circuit, open collector, or so on, or it's going to be directly pulled either to 5 volts or to ground, depending on the design of this trackball. The ones I'm using are either open circuit or giving a ground. So what I need to do on these signals is pull them high to 5 volts. And I do that with these pull-up resistors here. And I have a jumper that I would put toward this 5 volt V bus to act as a pull-up resistor. But if I had a different trackball where these signals are either disconnected floating or they're actually pulled to 5 volts when they're being active, then I need these resistors to be pull down resistors instead of pull up resistors. So I would put the jumper toward ground to make this a pull down network. And then by default, the signals would be all low when disconnected. And when this optical sensor asserts a signal, it's bringing it high to 5 volts. So I have this circuit duplicated. I'm calling this mouse 1, 2, and 3. And then I have some spare inputs. And also for mouse 1, I'm calling this just a left click and a right click button. ultimately, right now at least, in software, all of this is just like having 3 identical mice. I actually only have code written to look at mouse 2 because it was the easiest one to wire up on the corner of the board. And once I get that working, I'm going to copy and paste in the code to make the same thing happen on mouse 3 and mouse 1. So whichever one I'm plugged into, I could start using this and it will trigger movement on mouse 2. But if I had another one here for a different player, as long as we don't need simultaneous mouse interfaces, you can just use this one separately and it's still controlling the one mouse. That's fine. But long term, I would like to figure out if I can get the Raspberry Pi Pico to actually show up as multiple USB mice. And then I can separate these out and actually have simultaneous multiplayer trackballs if the game supports it. But currently, I don't know how to do that. So I just have it here in place in the hardware. If software ever allows it, I can get this implemented. And if I want to use one of these as an actual computer mouse, like the game emulator is going to be running on something, whether it's Linux or Windows. So if I just want to use, say, the trackball as the main mouse when I'm navigating around, I can hook up arcade buttons maybe on these mouse left-right buttons and just use this as a regular navigation within the OS. So that's what's happening on this circuit board with all of these inputs. And for now, I'm using CircuitPython. This is only the second thing I've ever tried in CircuitPython, so this is all hacking and slashing from other examples on how to do a USB mouse or keyboard, and then just learning as I go. So for the joystick inputs, these are switches, and they're going to have a lot of mechanical bounce, so I looked up how to use a debounce library, and I didn't even write code yet to do those mouse left and right click buttons. It's just penciled in here. And here's where I'm saying where is the X and Y axis for each mouse or whatever input. So there's 2 GPIO for X, 2 for Y on each of those 3 mouse inputs. So the X and Y each have 2 signals. And after going through this level shifter down to 3.3 volts, there's the GPIO they land on. So I am setting that up in the script. And regarding reading in these joystick switches, I have that debounce library set to debounce those pins for 30 milliseconds. It seems to be reasonable to let these switches settle. And I have this other number here. It's currently at 110 milliseconds. When it's time to send out a USB keystroke, because movement has occurred on here, what I found is if I press the button, so I send key X over USB, if I immediately release the X key then without a delay, just on the computer itself, it can pick that up. But once I was using the game emulator, it wasn't even detecting a key press. So I had to start adding a delay here. So I make a movement, it's time to send out X, but I have to let it keep being pressed for a certain amount of time. Then I can release that button press. Then it started showing up in the game emulator. So I'm controlling that here. And this starts adding a bunch of latency. Like we want this to respond as quick as possible. So I'm still trying to optimize this. I'm playing around with these numbers, but for prototyping right now, this is what seems to be working to get started. Really, I think this is all just software issues. I think part of my problem might be that I'm using CircuitPython. So maybe in the future I can change this over entirely to just using C in the Arduino IDE and using totally different code and routines, and it may work better. But in the end, I think this hardware is really going to stay the same. So I'm able to commit to this, and all of this stuff here on the screen here, this is all just me copying and pasting until something seems to work. So for each of those 4 inputs that I'm reading on the 2 joysticks, I set those up with button debouncers on all the GPIO that they ultimately go to on the board. And I have a few functions here to read in those 4 switches on each joystick. And here's where I'm converting it from reading in a logic 0, which is ground, over to assigning a logic 1 in some variable to show me which position the joystick is currently rotated to, and that translates to generating this table. So I throw a logic 1 in this position if input D on the schematic is what's currently the position I'm at. So down in the main loop, I'm always reading in both joysticks, and if nothing has changed, I basically have this result that's going to be -1. So if there has been a change on one of the joysticks, it's going to be some positive number, which is going to be either decimal 1, 2, 4, or 8, whichever position I just detected having entered. So I'll assign that new position to my current joystick position, basically, and I'm storing my previous good position. So now, every time through the loop, I can do the subtraction here and calculate, have I changed position from where I was to where I now am? It may not make much sense just trying to explain it line by line, and if I were starting over, this may not be entirely how I build up the signals into variables and figure out what I'm doing. I had to tweak this as I went, and this is just what I ended up with, so I kept it as is. So that's where I do the calculation and see, did we change positions in this kind of a table, and are we at a specific special case where we could have been going this way, then we wrapped around and started over again, and we need to calculate it differently. That all gets assessed once we have moved at all, and we're generating the USB keystrokes to say we went one way or the other if needed. Now, looking at the mouse, this is really not doing anything. If I were to click the left mouse button by connecting up the certain pin on here, it would just print out that I've detected the key press for now. Otherwise, I'm only really looking at this one mouse input on the second mouse channel. Again, this was giving me trouble. Like if I were going slow versus fast, it was just horrible. So I ended up deciding I'm going to set a threshold. Like if I make an x-axis mouse movement, I'm just using the regular mouse here now. If I go just a little bit to the right, I'm just going to move the mouse a little bit at a time. But if I suddenly realize I went this far after a certain threshold of movement, then I don't want this to go slowly and catch up to getting to there. I just want to start skipping ahead bigger amounts. So fine movements versus jumping to a bigger movement. This is just what I hacked up, and based on if I'm going slow or fast, left and right or up and down, this is the code that's doing that, but it's all just a disaster. So putting this all together, right now, this board is up and running. So if I have this trackball controlling the cursor, now I'm going only with this trackball, and of course it's choppier because trackballs allow you to go slightly up and down if you're trying to go left, right. So I can go very slowly under control, up and down, left and right, diagonal if I want. And if I try to zoom across, it doesn't go. If I do this again, really, it's hard to do this with a left hand too. Let's just go upward. So it went reasonably up. Now if I go slowly, it's going to take me a while to get all the way up. So that's what I was trying to emulate with acceleration. So that seems to be working. And now the text cursor is right here for the keyboard. So I'll put this here to indicate where we're looking. If I move this clockwise, I start generating one USB key press. If I start going counterclockwise, I generate the other keystroke. Now, like I said, between the debounce 30 milliseconds on these switches and my 110 millisecond long key press, I'm basically holding down one of these X's for 110 milliseconds and then releasing the keyboard key. So that's getting in the way of smooth operation here. So if I go out of the way here so I can start over, if I go only clockwise, I start going faster and I see here it registered a counterclockwise keystroke. I previously did this no problem with a Pro Micro as a USB keyboard and with ATtiny85 Digispark as a USB keyboard. And all I needed to do was have a debounce And within the libraries, it controlled how long to hold down the USB key, and it worked fine. So this one, it's reasonably okay, but it's bouncing incorrectly and sometimes going backwards when it shouldn't. I need to work on that, but generally I know the software is really what's causing these screw-ups in the joystick movement, and obviously the way I'm controlling this mouse cursor. Maybe it's perfectly fine for games. Maybe I need to optimize this. These are all software issues, but I think the hardware is good to go, so that's why I had these boards made, and now I can continue developing it as time permits.